Hi guys, welcome to the second lecture for calculus. Previously in calculus, I started the concept of limits. Therein, we were interested in figuring out what is the limit of a function, say fx, as x is tending towards a. Now, when we are talking about x approaching a, this could be from any side, either of the two sides, because we're working on one variable function. So we have x-axis and y-axis in the graph, right? So if this is some point A, the moment we see x tending towards A, it could be from either side of A. So it could be from this side. And we say that, as x tends to A, fx is tending towards some finite and unique value L. And that tells us that f has a limit, which is L, as x approaches A. But you know what? There are some functions whose behavior could change on either side of A. That's what today we will concentrate on. We call that one-sided limits. That is, to look at the limit of any particular function from each side separately, from one side at a time. I'm going to teach you this concept using an example here. fx equals to modulus of x upon x. If this is the function that we are considering, knowing that modulus x has a particular behavior, its absolute value of x, we've spoken about this before, which behaves like whatever is inside these two bars, that is the absolute value of x, x as it is comes out when x is greater than or equal to 0, and minus of x comes out when x is less than 0. I'm going to again put this point strongly here. For example, in order to understand this, just think of an example. If you're talking about modulus of minus 2, it's going to be minus of minus 2 because x is less than 0 here, and that means your absolute value is 2, right? So recall that. Knowing that this function will be equal to, since I can break modulus of x in terms of greater than, x being greater than or equal to 0, x being less than 0, so I can break this function as well. So let's create these subdomains. When x is greater than or equal to 0, this function will look like x upon x, and that would be equal to 1. Well, on the other hand, when x is less than 0, the function will look like minus x upon x, and that, my friends, would be equal to minus 1. What is this representing graphically? So we have, this is your y-axis, and say this is your x-axis. Let's try to graph this function and understand it a bit. So x is 0 here. This is your x-axis, this is your y-axis. X is 0 here. And the value of the function, as I can see, could be 1 or could be minus 1, right? So if you would like to graph it, it turns out like this. When x is greater than or equal to 0, that is at 0, you get this point, 0, 1. And even after 0, the graph looks like this. And when x is strictly less than 0, okay? Mind you, strictly less than 0, so there's no value here. But on the left, immediately left, you will have minus 1 throughout. So this is the kind of graph that gets constructed for this function. What's happening visually? What can you see happening here? X equal to 0 is such a point that the graph for the graph for this function is taking the value minus 1 throughout on the left of this point, 0, and it's taking the value 1 throughout on the right of this point, and at this point 0 as well. Can you see clearly there is a break? So which means that in case I would be looking at this function, let's understand this graphically and then we will be able to, nicely write down things about it. If I look at this function from a little left of 0, the values very minutely lesser than 0, I'm going to see that the function is approaching -1. On the other hand, the moment I will see the function approaching, the x approaching 0 from right of 0, that is, the value of x being just a little more than 0, I can see that the functional value or the function is approaching 1 at that moment. So what is it telling you? If you would visualize this function from the left of 0, the value turns out to be something else. If you would see this function, visualize this function from the right side of 0, the value of the function or the look of the function is something else. So you have two different values where this function is going around the same point 0 on the left and right. Okay, that's the concept of one-sided limits. Clearly what you can see here, as x approaches 0 from the right, values of fx, they're approaching 1. As x approaches 0 from the left, what you can see here, the values of fx approach the limit of -1. How would you write it? So we generally write it as limit x tends to 0 plus, when you're talking about right of 0 means a little more than 0, right? So 0 plus is the notation for it. Fx, which is modulus of x upon x, that clearly is equal to 1. Similarly, for the left, we write it as limit x tends to 0 minus modulus of x upon x is equal to -1. Now let's give it a general definition for any point x. So more formally, if the values of fx can be made as close as we like to some limit L by taking values of x sufficiently close to a but greater than a. So I'm talking about from the right. Then we write it down as limit. So this is the general point I'm taking, x tending towards a, right? So a plus, because I'm talking about the values of more than a. Limit of fx is equal to, we would say, that's equal to L. Similar manner, for the left-hand limit, if the values of fx can be made as close as we like to point L by taking values of x sufficiently close to a, but this time lesser than a, then we write it as limit x tends to a minus fx equals to L. And now let's connect the things. So we were talking about limit to a function as x tends towards a. When we just talk about x tends towards a, limit of fx, we're talking about both the sides. X could come from either of the sides, right? And then we spoke about one-sided limit. So one-sided limit means just from the left-hand side or the right-hand side. That is just little lesser than a, or x being little more than a, right? Now, what is the connection? Let's try to understand that. In general, there is no guarantee that a function f will have a two-sided limit given at a given point, say a. That is, it's not necessary that it is going to, fx will be approaching a certain value L every time as x is approaching a. That might not be certain. In that scenario, we say that limit as x tends to a of fx does not exist. Exactly the same way, it can so happen that the values of fx may not get closer to a single value L, single real number L, as x approaches from the right to a, or from the left to A. Now, in that scenario, we would say that limit as x tends to A plus fx does not exist. I'm writing D and E for does not exist. Or else it could be a case that it does not exist from the left. So as x tends to A minus the limit fx does not exist. Reiterating it again, I've always told you that whenever a function approaches a limit, this limit has to be unique in nature, right? Which gives you a condition for existence of the limit at a particular point. When will limit of the function fx exist as x is approaching A? It is only possible when, whether you see the function from the left-hand side, you get the same limit L. Whether you see the function from the right-hand side of A, you get the same limit L. Because otherwise, this would mean that I am getting two different limits. As x is approaching A plus, I'm getting a different limit. And as x is approaching A minus, I'm getting a different limit. So what will I take as the limit of the function? That has to be unique. I'm not getting anything unique, right? So that tells you when the limit does not exist. So with which you can figure out the criteria that when will the limit actually exist. Limit for any function at a point x equal to A, that is, as x approaches A, the limit of fx exists if and only if from the left and from the right, it is the same finite point L that f is approaching. So formally writing it down now. Therefore, two-sided limit of a function exists at a particular point A, if and only if both one-sided limits exist and have the same value. That is, what are we talking about? We're talking about limit x tends to A fx is equal to L if and only if limit x tends to A plus fx is equal to L and limit as x tends to A minus fx is also equal to L. That's the only scenario when the limit would exist. Taking you back to the example that I started off with. I started off with the example function modulus of x upon x. We know that this function is breaking up at 0 and we graphically saw what's happening. The function is approaching -1 when x is less than 0 and it is approaching 1 when x is greater than or equal to 0, which means from the left I have a different limit, which is this. From the right, I have a different limit, which is this. And from the left, I have a different limit, which is this. So we would say that left-hand limit, LHL stands for left-hand limit, at A, which is actually 0 in this case, is not equal to the right-hand limit at A. And that means that the limit as x tends to 0, fx, which is modulus x upon x, does not exist. DNE, which stands for does not exist. As far as when you're listening to me, you should know what I'm writing. So does not exist, DNE. Okay. Let us further look at some graphs and see whether the limit exists or not, or what can we talk about two-side limit and one-sided limits in these graphs. Clearly, with these graphs, we can talk about the following. We can talk about limit as x tends to A plus of this function fx. We don't have the functional form. I've just given you the graph. What is the limit as x tends to A minus of fx, right? So the first graph, the limit as x tends to A plus. For the first graph, I'm going to quote it as 1. So for the first graph, the RHL, the right-hand limit, is clearly, can you see the function is approaching 3? the function is approaching 3 from the right. And the function clearly is approaching 1 from the left. Clearly, the limit as x tends to a fx does not exist in this case, right? The second graph. In the second graph, the limit as x tends to a minus again is 1, and the limit as x tends to a plus again is 3. What's the difference between the two? The difference between the two graphs is that we have defined f of a here. In the first case, we have defined f of a as 2. On the other hand, we have defined f of a in the second graph. Okay, I have not written about the second graph yet, so I'm going to write it down here. Number 2. The second graph, I can see your left-hand limit is equal to 1 and right-hand limit again is equal to 3. And clearly, since they are different, so the limit does not exist. But what is f of a here? That's the different thing. F of a is equal to 1. In the third graph, what is happening is that we're not able to define f of a at all. The limit is still 3 from the right, 1 from the left, and therefore the limit does not exist. But f of a is not defined. That's the difference between the three graphs. In all the three cases, you can clearly see that the limit does not exist because the left-hand limit and right-hand limit, they are giving you different values, right? The learning point that you get from this example is that in all the three cases, the value of the function at a were different. And the value of the function, even when f is attaining a value at a, that does not guarantee existence of the limit. That's a very, very important point and takeaway from this question, okay? So, fa might not be defined, or fa might be taking two different values, as you can see here. The value in the first example, fa equals to 2, was absolutely different from whatever limits we were getting, one-sided limits. In the second question, the value that f is attaining is one of the one-sided limits, but still it doesn't give you limit at this point. The limit in any case does not exist for this function because the first right hand and left hand limits are giving different values, okay? Let's take another example, a quick example. So you have these three graphs here. We want to talk about the left-hand limit, right-hand limit, or the two-sided limit, whatever you can, give the information from these three graphs. Just try to write it down. So clearly in the first graph, the right-hand limit, that is x tends to a plus. X tends to a plus is also around 2. And a minus is also around 2. So what's happening? X tends to a plus, the function is approaching somewhat around 2. X tends to a minus, the function is approaching around 2 again. The value of the function at a is not defined. In this case, it has not been provided. So it is not defined for this function. It has not been provided. Okay? Whatever the functional form might be, we are not able to write down what is f of a, right? Whatsoever. Can you notice something? Your LHL is equal to RHL. So you would say that the limit as x tends to a fx, that's also actually equal to 2. It exists and it is equal to 2. In the second graph, the right-hand limit, again, from the right of a, f seems to be approaching 2. From the left of a, f seems to be approaching 2 again. So 2, 2. which means my right-hand limit and left-hand limit are same, and hence the limit of the function at this point A is 2. The difference is that between the two graphs is that we are defining the value of the function at this particular point A, and that has been defined as 3, which is different from the limit. That's another thing altogether. I'm not going to get into that topic right now in this video. We're just concentrating on the relationship between one-sided and two-sided limit. But since your left-hand limit and right-hand limit, they're equal, hence the value or the limit of the function at this particular point will be taken as 2, even when the value of the function is different, okay? The limit is 2. In the last graph that you can see here, from the left again, function is approaching 2. From the right again, the function is approaching 2. And the value of the function is also 2. Right side limit is 2, left side limit is 2. The value of the function is also 2. And the limit, because left-hand limit and right-hand limit are the same, it exists and it is actually equal to 2. So, well, again, take away from this question. This is a question where I gave you 3 graphs wherein the limit exists. Why does it exist? Because the left-hand limit at this particular point A was equal to the right-hand limit at this particular point A, right? Even when in one example, in one of the graphs, the functional value is not defined at this point A. In another graph, the functional value was different from the limit. And in the third graph, the functional value is same. So no matter what the functional value is at this particular point A, the limits may exist or may not exist. That's the takeaway from the 2 examples that we've done today. Thank you very much.